Okay, so exam one is moved to Monday. I just I can't be here on Friday, and I don't like to change things at the last minute like that. But
We do today, and then get like 150% early exam.
no, but thank you for asking. Um, so if it causes any difficulty to do it on Monday, or you have another exam Monday, and just anything, just talk to me, and I'd be happy to make accommodations for taking it another day. But I just can't be here Friday. So also no office hours on Friday. Yep.
So are we not meeting at all on Friday?
On Friday, no class. Right.
You can want to study stats for an hour.
Ooh, yeah, this room is open. That's a good idea. Study hall. Okay, so what I want to do today is just work on some problems, maybe just one. Well, I don't remember how long these take. But just rigid body statics problems where we're using centroid calculations. So the first one, this is a 2D one. We have a pin and a sort of L-shaped body. And it's held in place by this cable that makes an angle of 30 degrees with the horizontal. And then there's also a distributed load. And this is 2,000 newtons per meter. The dimensions this is 1 meter. This is 0.1 meters. And this is 1 meter. And that thickness is the same the whole way. So it's 0.1 meters along the top too. So we want to calculate, oh, and did I give a mass? Mass is 50 kilograms. And we want to calculate the reaction loads. Okay, well, we have to calculate the centroid of that shape so that we know where to apply the weight force. And then we'll deal with the distributed load after that. So if this is the shape, I'm going to put the coordinate system down in this corner where that joint is. I'm also going to put the about point there eventually. And so let's break this up into two rectangles. You could do it by subtracting one, but that means this top rectangle, I'm going to call that piece 1, and this tall skinny rectangle is going to be piece 2. For piece 1, the area is the length of 1 times the thickness of 0.1. So that's 0.1 meters squared. And the centroid of that piece is 0.5 for X. And for Y, so you're going to go from here, you have to go up 0.9 to get here, and then another 0.05 to get to the center. And then for piece 2, the area is, so the height of that thing isn't 1, it's 0.9. So 0.9 times 0.1 is 0.09. And the centroid of piece 2 for x is 0.05, and for y is 0.45. So the total centroid is 1 over the area of the whole thing. So the area of the whole thing is the two areas added together, so 0.19. And then the area of the first piece times its centroid. .5, 0.95. Plus the area of the second piece times its centroid. Tell me if you get the same thing or different thing. I got the centroid is 0.287. I'll call that 0.29. And y is 0.713. 0.7. So the centroid of this piece is not on the material. So now that we have that, well, I guess before I draw the free body diagram, let me also figure out the centroid of that distributed load. So we have this triangle that has a height of 2,000 and a width of 1. And so the area of that triangle is 1 times 2,000 divided by 2, so 1,000 newtons. This is newtons per meter, this is meters. And the centroid, so if you look back at the centroids of common shapes, for the right triangle, you go up to the the leg that has a height, and you go a third of the way toward the point. So that's 1/3 from the right toward the left. Since our origin is all the way at the left, that means that the coordinate, the x coordinate of this point, which is like here somewhere, is this 0.67. Okay. Okay, and for these, for the distributed loads, the y centroid does not come into play at all. So now we can draw a free body diagram. There's a weight force acting somewhere around here. that's equal to 490.5. The distributed load is acting here, 2/3 of the way from the left to the right, and the total is 1,000 newtons. And then you have a cable tension, and the pin joint down at this corner applies a full unknown force vector, so I'll call that R. Do we have any chance of solving this? If we have more than 3 variables, we don't, but in this case we have 3, so it should work out unless some of the equations are linear multiples of each other. You can, yes, there are simplifications you can make if you you think like, okay, maybe in this case, there probably isn't much you could do, but yeah, often I think if a joint produces a couple, like it does with the pin joints that share an axis, that couple doesn't end up being significant if there's something else preventing that rotation. So yeah, sometimes there are things you can do. Yes, the highest point is, that's what I think I said, 2,000 newtons per meter. But then the total point force is the area of that distributed load. Okay, so now the table, row, force, moment. So R, first of all, that's at the about point. The about point is going to be here. So row vector is 0. Force vector is Rx, Ry. Did I start this again? Cross product is 0. And then the weight force, the row vector is 0.29, 0.71. Those two components add up to 1. Do you know why that is? Just kidding, that's random. It just does. That's a total coincidence. Versus 0, negative 490.5. And the cross product is negative 142.25. And then the distributed load, the row vector is, so you notice you can move that force along its line of action, so we don't care about the height of that force. It's not going to come up at all. So it's 0.67, and then you can call that 1 or 0 or whatever, it won't matter. The weight force is 0, negative 1,000. Cross product is negative 666.7. And then the last one is the cable force. The row vector is 1, 1. That makes a 30-degree angle with the horizontal. So that vector you can represent as cosine of 30 times t. sine of 30 times t. So 0.866 t, 0.5 t. And the cross product is 0.366 t negative. Any questions about any of that? Okay, so now our equations. We're going to have three equations because it's two dimensions. The x equation says Rx plus 0.866 t is equal to 0. Our y equation says Ry plus 0.5 t is equal to, so it's Ry plus 0.5 t minus 1,490.5, but move that over to the other side. So it's equal to 1,490.5. That's the second equation. And then the moment equation says negative 0.366 t is equal to about 808.95. This is an easy equation to solve by substitution. Feel free to do that on a test. I'm not going to take off points, but you do need to start getting used to reduced row echelon form because pretty soon we're going to get into problems where you won't be able to do it by substitution anymore. Or if you do, it's just going to take really, really long. So let's write out a table, augmented matrix. We have three equations and three variables. So this is going to have 3 rows and 4 columns. I'll order it Rx, Ry, T, and then the constant. So the first equation says Rx is 1, T's 0.866, constant 0. The second equation, Ry's we have 1, T's we have 0.5, and the constant 1,490.5. The third one, T's we have negative 0.366. Constant is 808.95. Okay, well, we should be able to find that. So the moments. The weight force is going to produce a negative moment. That makes sense. The 1,000 is going to produce a negative moment. That makes sense. It shouldn't, I don't think, should it? It would hold it up, right? A cable there, that would hold it up. Okay, what's going on here? Okay, so sorry, I just turned that on, so had to change that angle, otherwise this problem doesn't work. And so now these are 0.5T, 0.866T, and now that cross product is positive. And so you get this for the third equation. And when you solve that, you get R is equal to negative 1914.1, positive 385.4, and the cable tension is 2210.3. Yes. Yes, thank you. The tension comes out the same because we didn't change that third equation, but the other two come out as negative 1105.1. And negative 423.6. So this is how you do it, for one thing. And then second, is there anything useful that we learned from this, or was that just a bunch of stuff that happened? This is what happens if you're designing something yourself, if you're working on something and you actually have to build this structure. This told us that our original configuration was not going to hold this thing. You know what I mean? there's no way to make that work with a 30-degree angle and a cable. So you can use these calculations to see whether this structure you designed is going to be able to be static or not. But mostly it's just a bunch of stuff that happened. Anyways, that's how you do it. Any questions about that one? Okay. Let's start another one, a three-dimensional one. I don't think we're going to be able to get through it, but so let's say we have this plate. Where this length is 0.6 meters. This is 1 meter. And then we've removed a piece like this, where that is a square with a length of 0.5 meters here and here. So that's a top view. And now the structure is set up like this. Let me move this down a little. Okay, you with me on this? And we have two pin joints. One here, let's say that they're all the way up against the two edges. And one here. And this is held stationary by, because right now it could just swing up and down, but it's held stationary by a cable that goes sort of diagonal across, where this is 1 meter. And the mass of this thing, question? No, the height to the connection on the wall is 1 meter. The mass is 60 kilograms. The joint on the left provides thrust, but not the one on the right. And we want to calculate the reactions. we have to calculate the centroid of this shape. What do we need that for? That's right. Yep. So if this didn't have the missing piece there, the centroid would be exactly in the middle. The weight force would be there, and that would produce a certain moment around whatever. Because this is missing, the centroid is going to move up this way a little bit, and that's going to change the moment that it applies.
That's just the subtraction in one direction.
Yeah.
Or addition.
Yeah, you could do it as adding 3 pieces or subtracting 1 piece. Okay, so first we have to calculate that centroid, and we can just do that as a 2-dimensional shape. The reason we can do it as a 2-dimensional shape is because it's a plate that has a uniform thickness everywhere. I'm going to put the coordinate system here. I guess I'll call this X, this Y, this Z. Maybe I do always do that. So this big rectangle, I'm going to call that piece 1. This little square, I'm going to call piece 2. The area of 1 is 0.6 times 1. The centroid of 1 with the coordinate system here. And by the way, like, be careful here because I have 2 totally different coordinate systems drawn, but I'm just using this one to come up with distances. And then I'm going to think about those distances in the real coordinate system of the problem. Yeah, that's right. So the centroid of that big rectangle is 0.5, 0.3. And then for that square, the area is 0.5 times 0.5. So 0.25 meters squared. The centroid of that thing for X, it's easy. That's just 0.25. For Y, we have to be a little careful because the bottom of that square isn't on the x-axis. This is up 0.05 meters. So it's going to be 0.05 plus the 0.25 to get here. So it's going to be 0.3. So the centroid of this thing is 1 over the total area, 1 over 0.85. Nope. Because remember, I'm subtracting. So the total area is going to be 0.6 minus 0.25. So 0.35. and then multiply that by the area of the first thing times its centroid. Minus the area of the square times its centroid. Since both of these two pieces have the same y centroid, we know that's what it's going to be. We didn't have to calculate that anyways because of symmetry, but I did. So let's see, 0.3. So I got 0.68. Anyone else get that? Okay, so this is 0.68, 0.3. Okay, so careful because this is a temporary coordinate system. We're just using that to find distances. Okay, so now that we have that, now we can draw the free body diagram. I'm not going to worry about the details too much on this. So now what loads are applied? Well, we know we have a cable force, T. We have a weight force that's acting somewhere out farther than the middle of that rectangle. That weight force is 60 times 9.81, so 58.67, right? 586.7. And then we have the two force vectors representing the pin joints. I'll call this one RA. That one has thrust, so that includes a force component in the z direction. And then the one here doesn't have thrust, so that only has x and y components. Call that RBX and RBY. And there are no couples on this because we have two pin joints that share an axis, so you leave the couples out. Oh, that's terrible. So let me just draw this dimension here. So what we figured out from the centroid was that this distance is 0.68. Okay. I'll finish this and I'll just put it on D2L, like with the class note link and stuff. But the only challenging thing we have left is we have to figure out how to represent that force applied by the cable. So we'll do that by coming up with the coordinates of that point, the coordinates of the point where they attach, subtract, make it a unit vector, and multiply it by t. Yep.
Yeah, okay.
Yep, should work. All right, that's it. So yeah, let me know if you want to talk over Zoom or anything. I'll be here tomorrow, but I won't be here Friday. Okay, bye.